All right, so here we go. We're just going to dive right into an example of finding the center of mass of in this case, a metal plate. All right, and then we'll sort of think, go back and think about it at the end and sort of generalize. But so in this example, we're given a metal plate with a constant density of 5 grams per centimeter squared, and the plate has a shape that's bounded by the curve y equals the square root of x, the x-axis, and x between 0 and 9. And x and y are measured in centimeters, which is good because our density is in centimeters, so centimeters squared. All right, so let's start by just drawing what this plate looks like, okay? So I'm just going to draw my axes, right? And you know what the square root of x, square root of x looks like. It would be something that looks like that. It looks like a parabola laying on its side. All right, and let's say that this is 9, right? So our shape is bounded by that curve. It's between 0 and 9 and the x-axis. Okay, so here's the x-axis. This is our y-axis. Okay, and y is equal to the square root of x is our curve. And so the first thing we're just asked to do is find the total mass of the plate, which is something that we can do. Let's just look at some slices, right? Now the density is constant, so in this case it really doesn't matter how we slice it, but it's always easy to integrate in the x direction, right? So if we slice it vertically, then the area of each slice is essentially x, or delta x times y, right? So then where y is equal to the square root of x. All right, so let me write that down. So the area of one slice is equal to y delta x, and so y is the square root of x, so it becomes square root of x delta x. Okay, so we can find the mass of one slice. So the mass of one slice, then we can just take it times the density, right? So the density is 5 grams per square centimeter, right? And all our dimensions are in centimeters, so that's good. So we're going to have 5 square root of x delta x is going to be the mass of one slice. And so if we want to find the total mass of this plate, we're just going to integrate from 0 to 9. So we're integrating in the x direction. And we're going to integrate these masses of all the slices, right? We're essentially going to add up all these slices and let the number of slices go to infinity. So this delta x becomes dx. So we're going to get 5 square root of x dx. That's our integral. So that's pretty easy. So we get 5, and then the integral of the square root of x is 2/3 x to the 3/2. And we want to evaluate that from 0 to 9. So what do we get? We get, let me pull the 2/3 out, this becomes 10/3. And then we're going to evaluate x to the 3/2 at 9. Square root, so the 1/2 part is a square root, so the square root of 9 is 3, and so we get 3 cubed, which is 27. And then of course at 0 is just going to be 0. So if we multiply that out, we're going to get 90 grams. All right, so we got the total mass. So if you recall, so the next thing we're asked to find is the center of mass. And if you recall, the center of mass, the denominator is the total mass. So we're going to need that. But in the numerator, we need the moments. Okay, so now in this case, if we take a look at this mass, now before we had point masses and we looked at the moments around the origin. Now to find the x and y coordinates of the center of mass, we're going to take the moments around the x and y axes. So if we look at this this slice that we were dealing with here, right, this little slice, we can find the moments around the y-axis And that is going to give us the x-coordinate of our center of mass. So that might seem a little backwards. We're finding the moment around the y-axis in order to find the x-coordinate of the center of mass. Okay, so essentially we're looking at tendency for any one slice to, to rotate this mass around the y-axis. Okay, and if we add up all those moments, all right, all the way down the x-axis, then we're going to get the center of mass, or sorry, the moment for this whole plate around the y-axis. Okay, so we're going to call that my. So the moment around the y-axis then is the integral from 0 to 9. Okay, now we have to find the moment of one slice. All right, so let me do that first. Moment of one slice. And it's really around the y-axis. Okay, so we're trying to find the moment of one slice, and then we're going to just add up all the slices. And to get the moment, we're just going to take the mass times its distance from the y-axis. And its distance from the y-axis is just x. So it becomes x times 5 square root of x delta x. Okay, so this is the mass. Oops, the mass. And this is our distance. Okay, so just like we had before, remember we added up all of the masses times their distances from the origin. Now we're going to add up all the masses times the distance from the y-axis, okay, in order to find the x-coordinate of the center of mass. All right, so now we're going to integrate this, all these moments to find the total moment of the plate. All right, so let's do that. So now if I take x times the square root of x, I get x to the 3/2. So I get 5x to the 3/2, and then as the number of slices goes to infinity, then this delta x becomes dx. Okay, so I just need to integrate that, and I'll have it. So let's pull the 5 out front, and then the integral of x to the 3/2 is 2/5 x to the 5/2. And we're going to integrate that from 0 to 9. And so what we end up with, let's see, these 5s will cancel. And so we end up essentially with square root of 9 to the 5th becomes 3 to the 5th. So we have 2 times 3 to the 5th. Which is 486. And the units here, right, we're taking mass times distance, so essentially the units are like gram centimeters, right? All right, so that's the moment. That's the moment about the y-axis, all right, for this whole plate. And then the center of gravity, the x-coordinate of the center of gravity then is the moment about the y-axis divided by the total mass. All right, so we end up with 486 divided by 90 grams, right? So then essentially it's grams centimeters, and then grams, so the grams will cancel. So you'll end up with the distance 5.4 centimeters. Okay, so that is the x-coordinate. Now, it's always a good idea to think, okay, does that make sense? So if you look at the plate, it's going to be heavier toward this wider end, this end toward the 9. So it gets thick, it gets wider or taller, I guess. The y-coordinate gets bigger as x gets bigger, right? So it makes sense, if it was evenly distributed. If it was just a rectangle, say, then the center of gravity would be like at 4.5. So it's always a good idea to look and say, okay, does that make sense? It makes sense that the center of gravity would be closer to the wider end of the plate because it's heavier on that end. So 5.4 is greater than a half, so okay, it makes sense. All right, so we also have to find the y coordinate of the center of mass. So we're just going to do something similar. So I'm going to scroll down here. I'm going to redraw my my mass, right? It's my plate. So this is 9, and this is y equals the square root of x. This is my y-axis. This is my x-axis. All right, so in order to find the y-coordinate of the center of mass, what we're going to do is find the moments around the x-axis. Okay, so and we're going to slice it in the opposite direction. Okay, so I'm going to take slices in this direction. So this is delta y. Okay, this distance here over to here is x. So the length of the slice is 9 minus x. Okay, but we want to integrate with respect to y now, because we want to find the moment around the y-axis to get the moment around the x-axis to get the y coordinate of the center of gravity. So I'm going to rewrite this as x equals y squared. Okay, so so now I can actually, let's find the area. Oops. Area. Let me go backwards here. Area of one slice. Okay, start with the area because we're going to get the mass, but let's start with the area. So it's essentially going to be 9 minus x times delta x, but it's not delta x, gosh, delta y, right? That's the thickness. But I really want to integrate with respect to y, so I'm going to replace the x with y squared. So it becomes a 9 minus y squared delta y. Okay, and then if we multiply by the density, then we'll have the mass. So the mass of one slice is then 5 times 9 minus y squared delta y. Okay, I'm going to scroll down just a little bit farther and give myself some room here. Running out of room. And we want the moment of one slice as well. The moment of one slice. So that's just going to be the mass times the distance from the x-axis, right? So, because we're trying to find the moment around the x-axis. So I'm going to write that down too. Around the x-axis. Okay, axis, yeah. All right, so I just want to take my distance in the y direction, right, times the mass. So that's just 5 times the quantity 9 minus y squared delta y. Okay, so this is again just distance times mass. All right, and then we're going to just add up all of these distances times mass to get the total moment. All right, so we want the moment about the x-axis in order to get the y coordinate of the center of mass. And we're going to integrate now. In this case, we're integrating in the y direction now, right? So this is 3, right? When x is 9, right? The square root of 9 is 3. So we're actually going to integrate from 0 to 3 because we're integrating in the y direction. And we're going to integrate y times 5 times the quantity 9 minus y squared. And then our delta y becomes dy, right? Because we're taking all these slices and letting n go to infinity. The number of slices go to infinity. So our delta x becomes dy. All right, well, let's clean this up a little bit. So integral from 0 to 3. Now, if I just distribute this y times 5, then I get 45 y minus 5y cubed. Okay, and then dy. Okay, well, that's not too bad to integrate. So I'm going to get 45 over 2y squared minus 5 over 4y to the 4th. And I want to evaluate that from 0 to 3. So I'm going to end up with, let's see, 45 over 2 times 9 minus, oops, I want a minus 5/4 times 3 to the 4th. All right, so if I just put that into my calculator, I get 101.25 grams times centimeters, right? That's my units. So that means I can find the y-coordinate of the center of mass just by taking the moment around the x-axis, so 101.25 grams centimeters, and then I'm going to divide by the total mass, so 90 grams. And when I do that, I get 1.125 centimeters. Okay. So again, does that make sense? So half of 3 is 1.5, so it would make sense that the center of mass is toward the wider end, which is going to be now the bottom, closer to the x-axis. So it does make sense. All right, let's sort of generalize here what we've done. So in general, for a region of constant density, so this is if it's the case where you have a constant density, some value, delta, then the center of mass is given by the integral of x times the density, so that's just a constant, and then this ax of x, so the function that represents the area of one slice perpendicular to the x-axis, dx. Okay, that's our moments. Okay, so that numerator, this is a numerator, and that represents the moment around the y-axis. Okay, and then we divide that by the total mass. Okay, now if we want the y-coordinate, then we're going to slice it in the y direction, right? So we're going to have the integral of y times the density times the area of a slice, right? The area of a slice perpendicular to the y-axis, dy, over the total mass. Now we could also do this in 3 dimensions, right? So if we had a 3rd dimension, then we could integrate and find the moment, and we'd have the distance z, again we have a z-axis in this case, times the density times the area of a slice perpendicular to the z-axis, z dz. Okay, now we're not actually going to do, there's no homework problems or any problems involving 3 dimensions. The most you're going to have is have to integrate 2 dimensions and find the center of mass of an object in just one of the dimensions. All right, now so you're going to be working with some 3-dimensional objects, but a lot of times we can take advantage of the symmetry of an object. For example, if you have a cylinder or a cone or something like that, then the cross-sectional area is a circle, and so that has a perfect symmetry, so we only have to really find the center of mass in 1 dimension. So let's see, I guess we have one more example here, at least one more, and so we'll we have one more before we go on. Now I know this video got a little long, and this next one is just basically introducing a kind of an alternate way of finding the y-coordinate of the center of mass.